So the last section for this course is going to be section 10.3. We're going to work on parametric equations and calculus. Most of my effort is going to be focused on finding the derivative of equations like this, that is the slope of the tangent line to a set of parametrically defined equations. So that's going to be dy by dx, and you can kind of get at that by a sneaky means, dy by dx. We can also rewrite this as dy by dt over dx by dt. So kind of a sneaky way to get at the derivative. And again, if you're using this notation going back to Leibniz, if you invert and multiply, you'll get the dt's to cancel out, and you'll end up with dy by, this should be dx here, dy by dx. Now, how do you find, say, the second derivative? Well, let's go through that. So d squared y by dx squared. So the second derivative. So that's going to be the derivative that is differential operator d by dx of the first derivative, dy by dx. And here we're going to play a little bit of trickery here. So I'm going to introduce a dt by dt term. And I still have my dy by dx term. And now I'm going to kind of shuffle things around a little bit. So d by dx. If I mix these things up, then I'll get that this is, let's see, I'll have the dt here and a dt here, and just move things around. I'll have dy here and dx here. Now, this can then be rewritten. This is this divided by this. So I can write that as, let's see, do I want to switch one of these one more time? Yeah, I'm going to rewrite this a little bit more. D by dt of dy by dx over dx by dt. And that's kind of the last stop. Basically, you're going to differentiate your first derivative and divide it by dx by dt. All right, let's apply this. And we're going to start with problem number 8. I'm going to try and find the derivative here. 8, you've got a parametrically defined function as x equals t squared plus 5t plus 4, and y equals 4t. Now, if you wanted to, you could eliminate the variable and get an equation in x and y. That's fine. You'd get a parabola. In fact, a sideways facing parabola. Let's see about graphing that on our graphing calculators. So to do that, we're going to change the mode on our graphing calculators. To graph this, we want to be in parametric mode. So hit the mode key, go down to parametric, and press enter on parametric. When you've done that, when you next hit the y equals key, you're going to get a different display than what you're used to. It's going to ask you for x of t and y of t. That is the functions that define each parameter, or defined by each parameter. When you press the x key, instead of getting the usual x, what you're used to, you're going to get a t. So t squared plus 5t plus 4. And then for y, it was just 4t. Kind of like our work in polar coordinates, we're going to rearrange things a little bit in terms of our work on the windows. Let's set up our window starting from, we'll start from 0 to 5. Your t step is going to be kind of like your theta step was for polar equations. So you don't want to make that too big. You don't want to make it too small. So 0.1 is probably pretty good. I would suggest that you let your calculator do the rest in terms of figuring out the values of x and y. You remember how to do that? What would we press? Zoom and then 0. Then your calculator will fit things, and you get something that looks like that. Which, okay, kind of hard to tell what that graph looks like. So if you'd like, you can expand things a little bit. Let's go from, say, -5 to 5, and then I'll do zoom fit again. Maybe I can see a little bit more of that graph. Okay, so you're seeing that it looks like a parabola, which is what we forecasted anyways. Let's compute some derivatives. So if I want dy by dx, then I'm going to calculate that as dy by dt over dx by dt. Let's start with dy by dt. What does dy by dt equal? Parth? What would dy by dt equal? 4. Thank you. Just the derivative with respect to t. And how about dx by dt? Anyone? 2t plus 5. Yay. Now, in this particular problem, I think they want the slope of the tangent line and the concavity at t equals 0. So if I want the slope of the tangent line, that's going to be at t equals 0, we're going to evaluate this function at t equals 0. So let's see what that gives me. Let's see. Well, it's going to give me 4/5, right? That's the slope of the tangent line. Yay. Let's go a little further and calculate the second derivative. What does the second derivative tell you about the shape of a function? Yeah, concave up or concave down. In fact, let's look at this one a little bit more closely. So we can make kind of a couple predictions. First of all, let's see if we feel that our prediction was correct on the slope of the tangent line. If we trace this at t equals 0, we get something here. Does that look like it would have a positively sloped tangent line? Yeah, looks reasonable. Something that, flows off of that. What does a concavity look like at that point? Concave up or concave down? Concave down. So my rough approximation to this for my Calc 1 students, concave up holds water, concave down spills water. So if your second derivative is less than 0, then it's going to be concave down. If your second derivative is greater than 0, it's going to be concave up. So what we need to do is we need to calculate the second derivative here. Now, our first derivative is going to be pretty handy here. We got to take the first derivative divided by dx dt and take the derivative with respect to t in that first derivative. So, wow, a lot going on here. Let me see if I can't pull that together for us. I need d by dt of the first derivative. So d by dt of 4 over 2t plus 5 divided by dx by dt. So divided by this. So dx by dt, let me zoom out a little bit. Dx by dt, well, we had it before. Here it is, 2t plus 5. Okay, well, joy. Guess what y'all get to use? The quotient rule. Ooh. A murmur of joy goes through the crowd. What's that? There is kind of a way around it. If you want to, then what you could do, d by dt, you could write that as 4 times 2t plus 5 to the negative first power. That's a way around it. And the 4 is a constant, so you can bring that out in front and then just differentiate it that way. So 2t plus 5 is just in the denominator. So how would that look? That'd be negative 4. So negative 4 times 2t plus 5 to what power? Negative 2 times what else? Times 2, because it's the derivative of the inside. So good question. Yeah, you can avoid using the quotient rule. Altogether, that would give me negative 8 times 2t plus 5 to the negative second power over 2t plus 5. Let's bring that down into the denominator. If I have 2 of them and then 1 more, I'll get negative 8 over 2t plus 5 cubed. Okay, so great. We avoided using the quotient rule. Probably not a bad idea. I know I teach this stuff, but I'm not really a big fan of using the quotient rule either. So, cool. Now, to determine the concavity here, let's see that it matches our expectations. We wanted to look at the concavity at t equals 0. So, at t equals 0, what would I get? I get negative 8 over what? 5 cubed, 125. Doesn't matter exactly what that is. The important part is that it's less than 0. So at that particular value, your concavity is going to be concave down. Concave down. Can anyone see a point where this graph is going to change its concavity? Where's the concavity going to change? It's going to change where the sign changes. Now, the sign can't change based on the numerator, can it? Numerator is always negative. But the denominator can change sign. Can you see where it can change sign? Yeah, negative 5 halves. So let's do a little trace here. Take out your calculator, hit the trace button, and let's see. So trace. Negative 5 halves is negative 2.5. Where did that put you? Where's that point land? It lands right on the vertex. And notice what happens. The function at that point changes over from concave down to concave up. So it changes concavity right at that point. Say what? Right there, it's neither concave up nor concave down. Yeah, it's right at the cusp. So, it's concave down from, let's see, concave down would be from negative 5 halves to infinity for t, and it's concave up the rest of the way from, is it negative 5 halves to infinity? Let's see, let me just check something. So 0, yeah. From negative infinity to negative 5 halves, that's where it would be concave up. So, yeah, but at negative 5 halves itself, it's neither, because it's actually got a vertical tangent at that point. Good question. Anything else on problem number 8? I think we got our money's worth out of that one. Cool. Let's try another one. Problem number 16. X equals 2 minus 3 cosine of theta, and y equals 3 plus 2 sine of theta. Now they're going to ask you to find the equation of the tangent line at each point given. They give you several. They give us negative 1 and 3. What else? 2 and 5. And one last tiny little regular ordinary point. 4 plus 3 square roots of 3 divided by 2, comma 2. So naturally we're going to work with just one point, and let's, I don't know, choose that one. All right. So we need to do a couple things. It's not a bad idea to kind of get an idea of what's going on with this graph, what's it going to look like. Can anyone tell just by looking at this set of equations? Well, let's practice something we did for our parametric equation, or our polar equations. That is, let's solve and get rid of the theta. Let's get rid of the parameter. So I can do that a couple ways. I don't like that negative there. All right, not much I can do about it too easily. So I'll move the 2 to the other side and get x minus 2 equals negative 3 cosine of theta. And then x minus 2 over negative 3 equals cosine of theta. And I'll do likewise over here. Subtract the 3. Y minus 3 equals 2 sine of theta. Y minus 3 over 2 equals the sine of theta. Cool. What's the last step there? What's my trick now to get rid of theta? Does anyone know? Remember from last week? Yeah. Square both sides and then add the results. So x minus 2 over 3 squared plus y minus 3 over 2 squared equals cosine squared of theta plus sine squared of theta, which of course is 1. Now, I was a little sneaky here. How come I can get rid of the negative here? I didn't like that negative, so I got rid of it. But how come I can do that? Yeah, because you're squaring it. Doesn't matter if you divide by 3 or negative 3. When you square it, that 3 is going to, or that negative is going to disappear. So you get something like this: x minus 2 squared over 3 squared plus y minus 3 squared over 2 squared equals 1. You should recognize that as an ellipse with a center at 2 and 3. I love my algebra students. They're in the habit of calling that an eclipse. So, all right. So it's an ellipse. I think I have that one graphed for us. Let's take a look. Parametric equations. Yeah. So here's the graph right here. I want to see if we can't find the equation of the tangent line at this point. 2, or is it? No, 4 plus 3 times the square root of 3 divided by 2 and 2, comma 2. So, boom, right there. Now, do you expect a positive or negative slope tangent line at that point? Positive. Yeah, definitely it's going to be something positive. So we're just going to have to figure out exactly what. But we expect a positively sloped tangent line right there. Okay, so let's find the slope of the tangent line. It shouldn't be too bad. So I need dy by dx, which is going to be dy by d theta over dx by d theta. And we're going to want to evaluate that at a proper value of theta. Let's start with dy by d theta. What's dy by d theta going to equal? Right, if you go up here and differentiate with respect to theta, it's going to be 2 cosine of theta. The 3 disappears with the derivative. So 2 cosine of theta. And likewise, we'll have 3 sine of theta. Remember, derivative of cosine is negative sine. So 2/3 the cotangent of theta. Great. That's the slope of the tangent line. We just need to figure out, well, where are we going to find the slope of the tangent line? What's the value of theta? So that's going to require a little bit of thought. If we're trying to find the slope of the tangent line at a particular point, well, we actually have two equations that we can work with. Either x equals this or y equals this. It's your pick. Which one would you rather work with? Would you rather work with x equals this or y equals this? Yeah, I think the y equation looks like a better choice here. All right? I mean, you're free to do what you want. But let's work with y. So that's going to be 2 equals 3 plus 2 sine of theta. All right, so 2 equals 3 plus 2 sine of theta. Definitely go for the easier one. So negative 1 equals 2 sine of theta. Negative 1/2 equals a sine of theta. Sine inverse of negative 1/2. What's that going to give us? Well done. I'm impressed. So there's really two solutions here. Let me remind you about that. Remember when you're solving an equation like this on the unit circle that you're really looking at the y-coordinate is negative 1/2. So something like this. So here's the line y equals negative 1/2, and it has two solutions. One here and one here. One in the third quadrant, one in the fourth quadrant. If you're looking at that, and somebody came up with the answer really quick, and I was very impressed. If you're looking at that going, I don't know those things, what you should do is take out your calculator and put it in degree mode. And keep in mind, calculus is done in radians. But it doesn't hurt to look at this in degrees, and you're going to get negative 30 degrees. That's this angle. If you go this way, that negative 30 is equivalent to 330, which is 11 pi over 6. Now the other possibility, this is also 30 degrees. 30 plus 180 is 210, and 210 is 7 pi over 6. So those are our two possibilities. How do I know which one I want to use? Do I want to use 11 pi over 6 or 7 pi over 6? Well, your graphing calculator can help you. You can just trace and determine which one you want to use. Want me to demonstrate that? Yes? Okay. So let's put in the functions into our graphing calculator. So it's going to be 2 minus 3 cosine of t and 3 plus 2 sine of t. What do you think a good range of values for t would be? Yeah, 0 to 2 pi, right? Because sine and cosine are periodic with period 2 pi. So 0 to 2 pi. What's the key step next? Set up your calculator's window by hitting zoom 0. So zoom 0 should fit. And now you can just trace. You can trace, if you hit the trace key and type in 7 pi over 6, as soon as you hit the 7 or any number, it's going to open up this window on the bottom. 7 pi divided by 6. That looks pretty good. We're going to get a point that looks a lot like what we're looking for. So 4.59, I'm guessing that would be the same thing as, where was our point? 4 plus 3 squared, so 3 over 2. Let's just type in, for good measure, the 11 pi over 6. 11 pi divided by 6, and it puts me someplace else. So the value of theta we want was 7 pi over 6. To be honest, I was a little bit surprised. I expected it to be 11 pi over 6. So good thing we checked. Okay, so let's plug in 7 pi over 6 into our function. It is into our derivative. So dy by dx at theta equals 7 pi over 6. That's going to be 2/3 times. Now let me go back to writing it as cosine of theta over sine of theta. Cosine of theta over sine of theta at 7 pi over 6. And I'm doing that because I don't know my values for the cotangent so well. So I'm making it easier on myself. I do know the cosine of 7 pi over 6. And I also know the sine of 7 pi over 6. Both of these are going to be negative because it's in the third quadrant. So it's going to be 2 times negative root 3 over 2 over 3 times negative 1/2. And the 1/2 will cancel. And I think that's going to be about it. The 1/2 and the negatives will both cancel. So it'll leave me with 2 square root of 3 over 3. That's my slope. That's the slope of the tangent line. Unless it's obvious, then yeah, I guess I would suggest you go back and check it. I mean, like I said and admitted, I was fooled. I expected it to be 11 pi over 6, and it turned out to be 7 pi over 6. So I guess it depends on how sure you are when you plug in that value for theta or t, whatever it is. So yeah, it's your call. Was there another question here? Yes. Those are equivalent. First of all, whenever we substitute into an equation like this, it would have to be in radians. So, it'd be kind of an interesting question here. And I don't think this is going to work on this one. If you type in, if we want to trace at negative pi over 6, I just don't know what's going to happen here. Yeah, see, it's not a value that we traced, because we only did values from 0 to 2 pi. So if I wanted that to work, I could set up my window from, say, negative 2 pi to 2 pi, and now it'll allow me to trace that point at negative pi over 6. So trace negative pi divided by 6, and it works. Well, you know what? It didn't exactly work, did it? Okay. All right. So, yeah, it's giving you an. Well, no, wait. I thought we should be over here though, shouldn't we? Okay. Yeah, negative 5 pi over 6. So, oh wait. Yeah, you confused me. All right. I actually expected that one to land over here. Why is it not working? Negative 30, 11 pi over 6, 7 pi. Oh, wait. All right. Yeah, so if we wanted it to work in a different way, we'd have to use negative 5 pi over 6. So let's try that one. Negative 5 pi divided by 6. That should bring us over here, and it does. So, but it only works now because I increased the size of my window. All right. There's good news, though. We're still not done with this problem. Yay! Isn't that awesome? All right. Well, what's left? We're asked to find the equation of the tangent line, right? So the equation of a line is given from this equation. Y minus y1 equals m times x minus x1. we've got everything we need. We've got our slope, and our point was given at the start of this. So that point had coordinates of 4 plus 3 square roots of 3 over 2, comma 2. So that's your x1 and that's your y1. If I substitute all that stuff in, it's going to be y minus 2 equals 2 square roots of 3 over 3 times x minus 4 plus 3 square roots of 3 over 2. Wow, pretty ugly. So y equals 2 plus 2 square roots of 3 over 3 times x minus 2 square roots of 3 over 3 times 4 plus 3 square roots of 3 over 2. So that's your linear equation representing your tangent line. I think this does clean up a little bit if you distribute and collect like terms. You can work this down to 2 square roots of 3 over 3x minus 4 over the square root of 3 minus 1. And I think that's the form that I chose to graph it in. Let me just take a double look here. Don't worry, I'll try not to give you anything this easy on an exam. I mean, something like that. All right. Let's see here. So, yeah. Looks like my line here, whatever it was, worked. And here's the equation that I used. Basically what I just put up there. So. Okay. Are we looking all right on that one? All right. A little bit messy at the end, I admit. All kidding aside, I wouldn't give you such nasty points to work with in terms of an equation of a line. You should be able to get the derivative and the slope of the tangent line. Are we okay on that much, Elise? All right, a little bit of love on that one. That's good. All right. What else here? Let's take a look at arc length. Arc length in parametric form. So problems like number 48 is what we're going to work with, but let me just take a quick look at the formula with you. It actually kind of comes from the Pythagorean theorem. You can see a little bit of it in here. And the derivation is something that I do take care to do in a Calc 1 class. I'm not going to take the time to do it now. Basically what happens is that you keep on approximating the length of these curves by little segments that come from the Pythagorean theorem. And it works out to your area, or excuse me, your arc length is going to be the first derivative squared of x and the first derivative squared of y. Add them up, take the square root, and hopefully this has been contrived to work out pretty nice so that you can integrate it. We'll do one example here. It's problem number 48. Let's kill these. And our goal is to find the length of arc of this function. Doesn't look very long, does it? Let me zoom in a little bit. And it still doesn't look long, because this is 1/2. And we're going to go from the point 0, 0 to this point right here, which is kind of strange. Pi over 6 and some function of the log, basically log of 3/4. All right. Let me write down a few things. Let's write down problem number 48 for ourselves and then do some work on it. Mostly what this is going to be is some practice of integration, a little bit of work with some of your old functions, logarithms, etc. x is the arc sine of t, and y is the ln of 1 minus t squared to the 1/2. Now I've taken a little liberty from the book. The book's not going to write this as 1 minus t squared to the 1/2 power. What would they use here instead? Instead of writing something to the half power, what else could you write? Square root. Yeah. Why do you think I wrote it with the 1/2 there? Yeah, it's just a little bit easier to take the derivative. In fact, I would apply the power rule right away. 1/2 ln of 1 minus t squared. This is going to be a little bit easier to work with the derivative that way. Let's find a couple derivatives first. dx by dt is simply going to be the derivative of the arc sine. So probably not a bad time to revisit that, as much as you've got a final exam coming up pretty soon. Who can show off? Derivative of the arc sine. Perfect. 1 over the square root of 1 minus t squared. Good deal. And the derivative of the natural log. So we can ignore the 1/2 because that's a constant. So it's going to be 1/2 times what? Very close. 1 over 1 minus t squared times negative 2t. Good. And the 1/2 and the 2 are going to cancel each other out. So it leaves me with minus t over 1 minus t squared. Okay. Not so bad. Let's see about calculating with these things. So I need to calculate the integral of a to b of the square root of dx by dt squared plus dy by dt squared, like that. Now, they tell us that t itself goes from 0 to 1/2. So I'm going to get the integral from 0 to 1/2 of the square root of 1 over the square root of 1 minus t squared, squared again, plus negative t over 1 minus t squared, squared. And that looks like a plus. It's really supposed to be a minus t squared. Let me just squeeze in a little. Let's use a little Photoshop to clean that up a little bit. So 1 minus t squared here. Ooh, shame on me, I almost forgot the dt. Okay, so a lot of work coming our way here. That's the integral from 0 to 1/2 of the square root of 1 over 1 minus t squared plus t squared over 1 minus t squared, squared again. Okay. What do you think I'm going to have to do to make a little headway here? There's nothing that I can easily do to integrate this until I clean up that radical. One more time? Can't really split them. It's tempting. I know that I've seen it on some exams a couple times. People want to say that the square root of a squared plus b squared equals a plus b, or in general the square root of x plus y equals square root of x plus the square root of y. Unfortunately, we can't split it up like that. Those don't really hold. So writing as a power. There we go. Well done. Need a common denominator. So the common denominator in this case is going to be this term squared. So what we're going to have to do is I'm going to have to multiply by 1 minus t squared over 1 minus t squared. So let's see what that does for us. That's going to be the integral from 0 to 1/2 square root of 1 minus t squared, right? Because 1 minus t squared times 1. And then 1 minus t squared again in the denominator, except this time it's going to be squared. Did that help us out a lot? Yeah, it really did. Okay, so the nice thing is that if you look carefully at the numerators, these two things add. In fact, I get a lot of nice simplification. I get the integral from 0 to 1/2 of the square root of 1 over 1 minus t squared squared. And that is helpful. Vicky, can you see anything that would simplify here? Thank you. You can just take the square root of that thing now. Wow. So some more review here for us. What would you integrate this as? Or how would you integrate that? It's not a bad guess, but it won't work. It's one of the techniques that we've learned in this course. And I can go through all the nitty-gritty detail if you'd like, or I can just show you the happy ending. But you need to figure out what technique is going to work here first. So Kevin got the last one. Someone else figure out, how are we going to integrate this one? What technique would you use? Think back in chapter 8. Let's see. So in chapter 8 we did integration by part, trigonometric substitutions, more trig substitutions, partial fractions, integration tables, indeterminate forms. Partial fractions, yes. So the trick is you could write that as 1 over 1 minus t times 1 plus t dt from 0 to 1/2. And yeah, you can do the rest with partial fractions. All right, I'm not seeing a whole lot of, oh yeah, in your eyes. So maybe I should do this one. What do you think? This is a nice case of partial fractions. So I'm going to grab a separate sheet of paper here and do it here. So it's going to be 1 over 1 minus t times 1 plus t equals a over 1 minus t plus b over 1 plus t. Boy, I should have wrote that with x's, shouldn't I? The trick in solving this is first to multiply both sides by the lowest common denominator. That is 1 minus t times 1 plus t, and clear out all the fractions. When I do that, this times the left-hand side, what's going to be left in the numerator? Yeah, 1 equals a times 1 plus t plus b times 1 minus t. Now there's a couple ways to solve this. I was poking my head in on one of my colleagues just the other day, and she didn't know the trick I taught you. Do you remember the trick I taught you to solve this? There's a couple ways you can equate coefficients, but the easiest thing to do here is to first of all set t equal to 1. What is setting t equal to 1 going to do for me? This term's going to be 0, so I'll get 1 equals a times 1 plus 1 plus b times, well, 0. So I get 1 equals 2a, or 1/2 equals a. So that's when t equals 1. Let's do it again, because I need to know what b is. Now I don't want to set t equal 1 again. Let's set t equal -1, because that's going to annihilate this term. So t equals -1. 1 equals a times 1 minus 1 plus b times 1 minus -1. That disappears. I get 1 equals 2b. So b equals 1/2. So both of those are 1/2. Yay! That means 1 over 1 minus t squared can be written as 1/2 over 1 minus t plus 1/2 over 1 plus t. That's what I wanted to get out of all this. So this is like 4 problems in one, which is really ultra cool. Let's finish this one up. So I want to take this result and plug it back into this integral. So it's going to be the integral from 0 to 1/2 of 1/2 over 1 minus t plus 1/2 over 1 plus t dt. I'm going to change this around a little bit. I'm going to factor out the negative from this. And let's factor out the 1/2 at the same time. So it's going to be 1/2, the integral from 0 to 1/2 of 1 over t plus 1 minus, because I'm factoring out the negative there, and I'm going to change the order of that. T minus 1 over 1 dt. I did that so I can integrate these directly and get logarithms. What's the integral of this? ln of t plus 1 minus ln of t minus 1 between 0 and 1/2. Now you can plug this in right here and work with it. I'm going to use the quotient rule for logarithms just to rewrite that one last time before I plug things in. So it's going to be 1/2 times the ln of t plus 1 over t minus 1 between 0 and 1/2. Plugging in a 1/2, I end up with 3/2 divided by -1/2. This is going to be -3. So it's going to be 1/2 of the ln of 3 minus the ln of 1, which is 1/2 the ln of 3. So that's 0. Whew. And in case you're curious, it's about 0.549. Probably should have absolute values here. Now we went a long way to get that answer. I don't think I'd put something quite so long on an exam. But if you do have a long problem, you get to the end, you might want to check it. You could check this number and compare it to what you get integrating this numerically. Just see if you get the same thing. It'd probably be a pretty good idea if you had a really long problem to double check it with numerical integration. How are we looking on that one? Yay! Let's take a break. When I get back, I'll give you some homework for this section.